So back to the VQE stuff and the optimization stuff. Now that I've done a bit of a detour with this control unitary building thing, so I wanted to kind of do a really short video first, trying to um, um, get a sense of what this paper is structured, like how is this paper structured, and because I wanted to go through these. Um, so Jared McLean shared it with me in the past, saying, that like it's it might be an interesting related paper for the stuff that I'm doing in terms of optimization, and I just wanted to kind of like I skimmed through this quickly. I wanted to read the abstract, and I wanted to kind of I saw there's a section because it's 30 pages. I saw there's a section called Summary of Topics and Outlines. So I'm thinking to do these today only. Just give it time enough, and don't just rush it too much because then there's optimization and quantum walks. There is exact solutions, crowbar, bigger transverse field, and hypercube graph. I don't really know exactly how to navigate the paper, so but it seems like it's really packed. And I wanted to. My goal is I wanted to take a look at and see if this paper kind of provides some more interesting insights into different optimization techniques or something like that. Maybe I have the wrong expectations. I don't know. It could be. So let's just go through these. Let's go through the abstract. So one of the major application areas of interest for both near-term and fault-tolerant quantum computers is the optimization of classical objective functions. We start on the right foot. In this work, we develop intuitive constructions for a large class of these algorithms. Okay. Based on connections to simple dynamics of quantum systems, quantum walks, and classical continuous relaxations. We focus on developing a language and tools connected with kinetic energy on a graph for understanding the physical mechanisms of success and failure to guide algorithmic improvement. Okay, so it's what I understand is that it's just trying to take example of stuff that's like naturally there in terms of physical effects like or physical stuff like the kinetic energy, and trying to take that into potential algorithmic improvements. Algorithmic improvements, I'm assuming it means in terms of existing optimization algorithms. So maybe it's not trying to come out with better or with new or different optimization algorithms, but try to improve current ones based on things like these. This physical language, in combination with uniqueness results related to unitarity, allow us to identify some potential pitfalls from kinetic energy fundamentally opposing the goal of optimization. This is connected to the effects from wave function confinement, phase randomization, and shadow effects lurking in the objective. I like how this sounds. And shadow effects lurking in the objective, far away from the ideal solution. As an example, we explore the surprising deficiency of many quantum methods in solving uncoupled spin problems and how this is both predictive of performance on some more complex systems while immediately suggesting simple resolutions. Okay. Further examination of canonical problems like the Hamming ramp or Bush of implications show that entanglement can be strictly detrimental. Interesting that entanglement can be strictly detrimental to performance results from the underlying mechanism of solution. In approaches like QAOA, so is this saying that entanglement can actually hamper the optimization? I thought that was something you actually wanted to have, right? You wanted to have in your ansatz, right? In terms of you have entanglement in there. Interesting. Kinetic energy and graph Laplacian perspectives provide new insights to common initialization and optimal solutions in QAOA, as well as new methods for more effective layer-wise training. Okay, that can be interesting. I think that just makes worth the 30 pages. I'm not going to go through this sequentially, I guess, and it's going to be multiple videos probably, but I just, kind of before going back and kind of wrapping up the whole portfolio optimization, I just thought it was interesting to take a look at this kind of stuff, just beyond, beyond what's standard VQE, beyond like the how's it called? I forgot the name. the fact that you can differentiate by like subtracting the expectation values with shifted parameters. Where was I? Connections to classical methods for continuous extensions, homotopy methods, and iterated rounding suggest new directions for research in quantum optimization. Throughout, we unveil many pitfalls and mechanisms in quantum optimization using a physical perspective, which aim to spur the development of novel quantum optimization algorithms and refinements. Sounds quite interesting. It really sounds interesting, at least promising. I think I'm going to keep the introduction for now. I'm going to skip the introduction for now. Gross algorithm, quantum walks, blah blah blah. Optimization topic. It's a broad topic. Um, Parents being less problems. I don't know. If the direct use of Grover is to make any impact on optimization problems, it is likely to be in a narrow window of problems. Using a more modern interpretation of Grover's search and amplitude amplification has led to asymptotic speedups of structured classical algorithms like annealing and branch and bound, but the overheads for general cases remain challenging. And the fact that real use cases have shown that it is likely the case that improved solutions are most needed on problems with over 1,000 beats, where classical heuristics break down. Connections to searching by continuous time quantum walks have provided better bases. I've never done quantum walks. I should do that. I've never done quantum walks. I don't even know what a classical random walk is, you know. Is a mathematical object known as a stochastic or random process that describes a path that consists of a succession of random steps in some mathematical space that just... okay. It's literally a random walk. It's literally a random walk. Random walk algorithm. Okay. Interesting. So it's just I guess, generalization of just like randomly finding a solution to something, and then there's probably a quantum version of these. Okay. Let's just I basically skipped the introduction. I just wanted to understand maybe what's the summary of topics and outline, and I'll just leave it here because I don't have much time. I just wanted to kind of have get started with it. So in order to better organize this work for can you read this one? Yeah. In order to better organize this work for the time-conscious reader, we attempt to outline the general topics of discussion and conclusions from each section in section 3. Okay, so section 3, there is the general topics of discussion and conclusions. So there could be another section to jump to. Okay, so that's where we should probably go. We'll begin with a review of optimization and connections to the language of quantum walks. We highlight the formulation of several popular approaches such as quantum annealing, adiabatic optimization, and the quantum approximate optimization algorithm, QAOA, in a way that allows them to be simply connected and generalized in the language of graph Laplacians. Okay, so basically what they do is they make a connection to whatever this is. Not a Laplacian matrix, although that's something interesting as well. Oh, there's even like intuition. It seems like the Laplacian matrix is related to that. Okay, so is this gonna have to No, that's not Lagrange, that's Laplace. Okay. Oh, so this is it. So in the mathematical field of graph theory, the Laplacian matrix, also called graph Laplacian, admittance matrix, Kirchhoff matrix, and or discrete Laplacian is a matrix representation of a graph. Okay. The Laplacian matrix can be used to find many useful properties of a graph. Together with Kirchhoff's theorem, it can be used to calculate the number of spanning trees for a given graph. What is a spanning tree? This parses cat of a graph can be approximated through the second smallest eigenvalue of its Laplacian. Oh god, that relates eigenvalues and graph stuff. It can also be used to construct low-dimensional embeddings, which can be useful for a variety of machine learning applications. Well, that seems like something worth taking a look at, right? I love how a lot of this stuff is like, hey, if I take these and I represent it like that, then I can see different things and then I can relate stuff. That's really cool. So so there's going to be a bunch of relations here built. Yeah, that that can be. It's just so easy to get lost in all these, and I just so it sucks, but yeah, it's also enjoyable. Following these, in section 4, we take common cases from the literature and using properties of unitarity. What is unitarity? Is it just something special? Is it related to, like in quantum physics, unitarity is the condition that time evolution. Okay, it's by unitary operator. I assume that that's what they meant. Demonstrate a number of exact results on problems solvable in extremely short depth. We show that the Grover driver, or complete graph Laplacian, represents an extreme of too many connections, preventing any structure in a problem from being exploited in a meaningful way, and that this construction is in contrast with other possible choices for the graph, and these constructions in contrast with other possible choices of the graph. Okay, Grover driver. That is a fancy. Mm, yeah, that's probably not what I'm. That's not probably something I can easily Google. Um, so the graph Laplacian of that, I guess that's what they meant. Give me a second. Gotta get some. I think refill coffee. Okay, I'm back. Where was I? Using this information, we identify a mechanism of solution in short-depth algorithms like QAOA and construct a mean field variant to exhibit its properties in section 6. So wait a second. So is this saying that what they do is they use these, so they use this graph Laplacian to show. Oh, I think I skipped the. Sorry, I think I skipped this whole section here. They take with this graph Laplacian thing, they take common cases from the literature and using properties of unitarity demonstrate a number of exact results on problems solvable in extremely short depth, and then show also that there's some extreme of too many connections preventing any structure in a problem from being exploited in a meaningful way. We go on to show that existing methods can fail to solve uncoupled spin problems in surprising ways. While some of these results are known in the literature, our exposition aims to increase clarity. I like that. These constructions lead us to analogies with problems of scale like ill conditioning and gradient descent classically, and methods for preconditioning problems to avoid these difficulties. That's also interesting. This brings us to a more general connection to continuous extensions in section 5 and the relation between VQE and the classical multilinear extension. Whatever that is. In practice, we see that many methods for variational circuits used on discrete optimization problems share commonalities with classical techniques often used in approximation methods and belief propagation. The similarities motivate the introduction of a technique from classical approximation methods, iterative rounding, okay, which addresses problems of scale, quantum classical readout challenges, and underlying challenges related to symmetry. A connection is also made to the classical theory of homotopy methods for global optimization, which bridge the quantum adiabatic method. We identify a mechanism of solution in short-depth algorithms like QAA and construct a mean field variant to exhibit these properties in section 6. There's some sort of like majority of vote. In particular, several of the canonical problems studied, such as the spike bones. What else? This global consensus model reveals a particular class of failures that can occur within quantum optimization methods. We term them shadow effects. In particular, energetic defects distant in Hamming weight can have considerable influence on the ability of variational methods to effectively refine their solutions due to the global nature of evolutions. That would be interesting to understand what the shadow effects are. Simple examples, where this is the case, and the impact on the efficiency of algorithms. Our conjecture is that this phenomenon is an underlying mechanism related to concentration of measure observed in the QAA landscapes for random problem instances. So you modify the objective function, you can avoid some of these issues. This brings us to the crucial underlying element of kinetic energy in quantum optimization. Okay. Kinetic energy from the confinement of a quantum optimization based on the real Hamiltonian presents a force fundamentally opposed to the goals of classical optimization. Insights from kinetic energy allows us to understand why so many optimal paths in QAOA resemble smooth deformations, why initial gas paths from adiabatic schedules are often crucial for success, and why layer-wise greedy optimizations are so challenging. We offer techniques for circumventing these challenges, such as weighting the kinetic energy while training layer-wise or searching for new variational components. That's really interesting. So, but what has got kinetic energy to do with these? I have absolutely no idea. Potential energy transferring into kinetic energy, yeah. But like quantum kinetic energy. What else do we have here? We investigate numerically the impact of these issues and basic techniques of remediation on common models like ferromagnets and maxcat. In analogy to non-interacting systems, simple rescaling can destroy the performance of some algorithms on systems like a 2D ferromagnet. We also show substantial depth is required to reach a classical baseline from a simple classical continuous extension. In section 10, we tie together our conclusions to make general recommendations for the improvement of low-depth quantum optimization and close with thoughts and outlooks. Cool. So what I will do is, next video, I'm going to read the third chapter where they just go through, I think, the main results and all the stuff. And I'm trying to understand a bit more about this. Doesn't seem too heavy, but and it talks about graphal ablations. So I think that's going to be definitely something interesting to learn about in terms of, you know, what properties do we uncover when we change this kind of, you know, representation. I mean, how is that though? So they make a we highlight the formulation of several popular approaches such as quantum annealing, adiabatic optimization, and the quantum approximate optimization algorithm in a way that allows them to be simply connected and generalized in the language of graphal ablations. Okay, so what they do is they talk about quantum optimization using the language of graph Laplacians, I guess. And what is the kinetic energy here? So in physics, the kinetic energy of an object is the energy that it possesses due to its motion. It is defined as the work needed to accelerate a body of a given mass from rest to its stated velocity. Having gained this energy during its acceleration, the body maintains its kinetic energy unless its speed changes. The same amount of work is done by the body when it's decelerating from its current speed to a state of rest. In classical mechanics, the kinetic energy of a non-rotating object of mass m at a speed v is this. In relativistic mechanics, there's an approximation. And what about quantum? Several mathematical descriptions can exist that describe an appropriate physical situation for objects and processes in common human experience. However, if the speed of the object is comparable to the speed of light, then relativistic effects become significant. If the object is on the atomic or subatomic scale, quantum mechanical effects are significant. The quantum mechanical model just must be employed. In quantum mechanics, here you have. In quantum mechanics, observables like kinetic energy, oh, that's an observable, okay, are represented as operators. Ah, cool. So we're learning about some new observables, not just like the position, momentum, and what was the other one? Yeah, whatever. For one particle of mass m, the kinetic energy operator appears as a term in the Hamiltonian and is defined in terms of the more fundamental momentum. It kind of makes sense, yeah. The kinetic energy operator in the non-relativistic case can be written as. Notice that this can be obtained by replacing in the classical expression. Okay. In terms of momentum. In the Schrodinger picture, takes the form, whatever that is, where the derivative is taken with respect to position coordinates, and hence okay. I have an idea. The expectation value of the electron kinetic energy for a system of n electrons described by the wave function psi, whatever, is the sum of one electron operator expectation values. Mass of the electron, me is the mass of the electron, and this is the Laplacian operator acting upon the coordinates of the ith electron, and the summation runs over all electrons. The density functional formalism of quantum mechanics requires knowledge of the electron density only. It formally does not require knowledge of the wave function. Given an electron density, the exact n-electron kinetic energy functional is known. However, for the specific case of one electron system, the kinetic energy can be written as, where this is known as the von Weizsäcker kinetic energy functional. What is a functional? I've read this somewhere. Why I have caps on? The term functional has at least three meanings. It refers to a linear mapping from a vector space into its field of scalars. It refers to an element of the dual space. Okay. From space X to real numbers. In computer science, it's terms of higher order functions, functions that take functions as arguments or return them. Okay. Okay, cool. So we're gonna I'm looking forward to understanding a bit more about the kinetic energy as an observable, and see how this whole graph Laplacians kind of thing here. What does this bring to this whole optimization? But I see it's not about new. I mean, there is something. So there is a mixture, I think, of insights and then something that can come at least new for me, which is the whole kinetic energy stuff. So we'll see. but it definitely seems an interesting paper. But I just have to dose it because it's really 30 pages, and I think I have to kind of like, otherwise I'll get easily lost into these. And it's a big paper. And one thing that I like to do is I like to maybe, you know, uh, read some of the stuff, not everything maybe, and then try to take it back to VQE and see if we can um, play a bit with these and the portfolio optimization paper from multiverse computing. Cool. Yeah, so some more reading videos coming soon.